before starting the today's lecture, I would like to mention a few things. So like for the past few days, we had been talking about several topics related to spatiotemporal data mining. So we talked about the missing value prediction. After that, we talked about extreme value analysis. Then yesterday we talked about networks. Today we will also talk about two more topics. So with that, we will come to the end of our spatiotemporal data mining part. So in like earlier like we had already covered spatiotemporal statistics, under which we covered all those Gaussian processes, the geostatistical equation and all those things. So based on which you had an assignment also. And I hope you remember that by next week you should be submitting that assignment. And I expect the assignments to be submitted. I mean, a report to be given in either in PDF form or in the Python notebook format, properly annotated, so that like one can easily understand the plots and everything which you have got. And I like for these lectures, you have also been invited to make the scribe notes. I have not received any scribe notes so far, but like like you can submit any scribe note for any lecture up to within say 2 weeks from the date of the lecture. So if you are planning to so again, for nobody, scribing is mandatory, but like 5 marks are available for that. So like it is expected that everyone will scribe at least one lecture. And next Monday we will have a problem solving session where we will work out some numerical problems related to the spatiotemporal data mining topics which we have been and the spatiotemporal statistics topics which we have covered so far. And on the following Monday, which I guess will be 21st of February, we will during the class hours 2 to 3 p.m. we will have the first test. So that in the test we'll mostly have numerical problems. So before that, to prepare you for that, in the following Monday, which is 14th Feb, we will have the uh, we will have have a brief problem solving session, and some solved problems, or some practice problems will also be provided. And yeah, and after that we will move into the next part, where we will be discussing various case studies of the application of these techniques or related techniques to various problems related to the geosciences. So and during that period we will also have some guest lectures. And as you had been informed initially, in this subject you will be required to give a seminar and also do a project. So the seminar topics and the project topics, I will give a few seminar and project topics from which you can choose, and otherwise you can form your own topics also. So by the end of this week, I will provide a list of seminar and project topics. And you will be expected to have finalized these your seminar and project topics by say 22nd Feb. So I said 21st Feb is the date of the exam. Soon after that, you should finalize these things. The project is to be done in groups of four, up to 5 students. The seminar is to be done individually. And so in case the seminar, we will not actually have to present it during the class hours because we do not have so much time. So what you will do is you will record, you will prepare the slides, you will record a video and share the link with me for evaluation. In case of project, the details of the project will be discussed a bit later. But I will give out the project topics, and I will expect you to do a brief survey of what the topic is about. I mean, what kind of data sources are available, etc. I will not provide any data sources. in some cases I may in most cases I will not. So you are expected to search some literature and identify some data sources for that topic, and based on that you can you can do the you can start the work in the once your project has been assigned, and once we have once your team is formed. So by 22nd of February, I will expect the project. You have to have formed the project topics. The second assignment will be also be given sometime later next week, once you have submitted the first assignment, and you will have again 2 or 3 weeks of time. So that is so regarding the evaluation, by the end of February, we should have covered uh, the test as well as two of the assignments, and after that in the remaining parts you are expected to work on the the seminar and the project. Okay. And if you can and just to remind you about the scribe notes, so they are worth 5 marks. So you can choose your topic, and you can start sending it within 2 weeks of the corresponding lecture. Okay, so with that, let's come to the topic for today. So today we will cover two topics related in the domain of spatiotemporal data mining. So first of all, I'll talk about spatiotemporal anomaly detection. So, we had briefly talked about anomaly detection, like earlier also. Uh, so we had anomaly. We had defined in in this way. That is basically the deviation from the mean behavior. So for at any given location and time, we had like mu st is what we called as the climatology, or that means at that location and that particular time there is a historically normal observation. I mean the historically normal value, and any given observation we have to see how different it is from the corresponding observation. I mean the corresponding historical value, and that amount is the anomaly. Now these so that is the so in case of earth sciences, this is the definition of anomaly, but in case of data sciences it simply means the deviation from other values. Okay, so those of you who may have done some projects based on anomaly detection and so on, for them the anomaly detection basically meant identification of or location of unusual measurements. So in this case, since the data set we are talking about, or the type of data which we are talking about is the spatiotemporal data, so the anomaly in this case, the spatiotemporal anomaly will mean the deviation from the values of the spatiotemporal neighbors. So like at any given location and time, we have an observation. Now, like in some of the earlier classes, we have discussed that there is usually in most cases because of the properties like spatiotemporal autocorrelation, uh, because of the spatiotemporal autocorrelation, we usually see that the neighboring values in both space and time are usually closely related to each other. So we do not really at a given time point, we do not really expect two locations which are neighboring to have significantly different values of the same variable. And on the contrary, at the same location, at two time points which are close by, we do not expect to see large changes of the any kind of variable. That is, there a change over time can happen at an hourly scale, at a daily scale, at a monthly scale, and so on. But still, at whatever time scale you are considering, we do not usually expect a very large jump. That is from the temperature at uh, 10 p.m. is likely to be greater than the temperature at say 11 p.m., but we do not expect a very significant change. Similarly, the mean temperature today is not expected to be very significantly different from the temperature tomorrow or yesterday, and so on. So if such a thing is happening, that is this, if you see a location or a time where this property is being violated, that is there is a large deviation, then we can call it as a spatiotemporal anomaly. So such spatiotemporal anomalies can be either isolated or bulk. So the isolated means there is like at only a single location or at a single time point there is this kind of a deviation which is easy to detect, or it can be bulk where on a like at a given time point or at a given at a given time point there are many locations where there is this kind of a like deviation, significant deviation, or like at a given location but spanning over several days or several time points there is a significant deviation. Yeah, so such things are known as, refer to them as bulk anomalies or anomaly events. So for that purpose, let us look at this spatiotemporal data set. So this data set, like in a sense, it is somewhat similar to the data set we had considered last Monday when we are considering missing values. Now here there are no missing values. Instead, there are anomalies. And like it has also been told to you that S1, S2, S3 are one set of locations which are like close to each other, and S4, S5, S6, these are another three locations which are close to each other. Okay, and these are consecutive time points. So based on this matrix, can some of you identify some anomalies, either isolated anomalies or bulk anomalies? Yes, anyone? Can anyone? Can Can anyone identify any anomalies?
Sir, in S5, T3 can be T3 and T6 can be anomaly. Oh, sorry. No, no,
Teeth.
sir.
Okay. Yes, any? Could anyone spot anything?
In T3, S1, 22, and
So
S3,
T3,
20.
S3,
T3? Which location?
S3.
S1 and
T
S3.
T3 S3. Okay, fine. So 20. So this value you can see is significantly different from its temporal neighbors at the same location, as well as it's different from its spatial neighbors at the same time. So yes, so definitely this one is an anomaly. So there are some other anomalies also. So this is so like as you can see, this is a kind of an isolated anomaly. That is, its immediate neighbors do not seem to be anomalies. Can you spot any bulk anomalies where several locations or several time points seem to be having an anomaly simultaneously? But this one is definitely an anomaly. Okay, so another anomaly is like you can consider this as an anomaly. So here you can see that it's the difference of its values with its spatial neighbors is quite. I mean, sorry, at the different temporal neighbors is large, and with spatial neighbors also it can be considered to be large. But depending on what threshold you are putting. So like for example, from here to here, the difference is, so from here to here, the difference is 6. So if you have set a threshold of say about 5, then we can say that this one is also an anomaly. But like if you see here, these two values 30, 31 and 32, 33. So here if you see, like in these two values, so 30 is very different from the previous values, say 24, 26, 22 at the same location. And similarly, it's also very different from the subsequent values 23. So we can say that there is something like a bulk anomaly here, that for two successive time points, there is like a large change there, after which again it comes back. Again at T5, you can see that both S1 and S2 are having this kind of an anomaly. In S1 already had it from the previous uh, time point. Now at T5, S2 is also getting an anomaly. And in T6, the anomaly in S1 is over. Now it is back to its standard value. But in S2, it is still continuing. What started in T5 is still continuing. So it's like something, an anomaly event started in S1 at time T4. At T5, it infected location S2 also. Now in S1, it got over at T5, but in S2, it continued is continuing in T6. So like it's like, let us say that some kind of a heat wave is there, which is propagating from one region to another. In region 1, it affected days T4 and T5, after which in T5 it moved away from location S1 to location S2. So this can be considered as a bulk anomaly. So similarly, you can, like if you scan the whole data set, you will find more such as isolated or bulk anomalies like this. So the question is how to uh, how to detect some such anomalies. What is the anomaly detection algorithm? So there are, of course, several ways. The simplest approach is obviously to compare with the spatiotemporal neighbors, or with the climatology using some kind of threshold, which is what we seem to be hinting at here. Like at every time point, you consider the differences between like neighboring locations. If you see that their difference of the observation is above a threshold, then you have to understand that at least one of them is having an anomaly. Now, which one of them is having an anomaly? That is, if you consider 29 and 20, their difference is of course 9. So that means some kind of anomaly is involved. But is 29 the anomaly or is 20 the anomaly? So for that, you will have to consider it's the temporal neighbors also. So as you can see, 29 is not different from the like at the same location. 29 is close enough to the values at the neighboring time points. But in case of 20, if you look at its temporal neighbors, the difference is still quite large. So we can say that 29 is not the anomaly, it's 20 which is the anomaly. Okay, so this way we can try to localize the anomalies by comparing with spatial and temporal neighbors. So this is one approach, but this has certain obvious problems. The obvious problems include that first of all, the results are totally sensitive on threshold. So if your threshold is say 9, then this is an anomaly. But if your threshold is 7, then this like or sorry, if your threshold is 9, then this is an anomaly. But if your threshold is say 10, then this is not an anomaly. Similarly, this cannot just comparing with neighbors will not be able to catch the bulk anomalies, because bulk anomaly is a situation where the neighbors are also affected with the anomaly. So just by comparing, if you compare with the neighbors, you will not be able to catch them. And in many cases, the climatology or the standard value you may not be available. You simply may not have so much of data to calculate the climatology. So then what will you do? So there are basically two broad approaches. One is based on clustering algorithms, and the other is based on latent variable models, which like basically you have to uh, define some kind of a probabilistic model for the data, and you have to see which of the values can be like have high probability under that model and which values do not have high probability. So that is these are the two possible approaches. So let us first talk about clustering. So when we talk about clustering, we talk about usually talk about say k-means clustering and things like that. But k-means clustering does not work well for anomaly detection, because like anomaly is something which is like which is by definition which is rare, and it's not that. And so what k-means will do is it will try to break up this data set into some similar sets of similar values. So like for example, and these locations and these time points, they have similar values, so these can form one cluster. Maybe these also. Then again here it will try to form a cluster and so on. But but there is no reason to think that these uh, anomalies or which we are considering as anomalies, like they will be part of some other cluster or some separate cluster or something like that. I mean, it can happen, but it may not happen either. So, I mean, what I am trying to say is that K-means is not particularly equipped at identifying anomalies. Besides, K-means has a big problem. We have to specify the value of K. Now, in this kind of a situation, there is no basis for specifying any value of K. That is if we say that K equal to 2 means that I need two clusters, one for anomalies and one for the normal values, k-means will not give you any meaningful result. That is because the different anomalies which are present in this data set, those anomaly, it's not that those anomaly readings are close in value. Like for example, this 37, this is like this is a large value, this is an anomaly, but 20, which is a small value, that is also an anomaly. Then again, 30 and 31, in this case, these are anomalies, but 30, 31, if they occur here, then they are not anomalies. So k-means will not be able to capture these kinds of nuances. So we do not go for that. So instead we go for other kinds of clustering algorithms. The type of the clustering algorithm which is most commonly used for this kind of for the anomaly detection task is known as the DB scan. So this is like it's a case of what they call as a non-parametric clustering algorithm. So what happens here is the basic idea is as follows. So it's actually it's called a density based spatial clustering. That this is the full form of DB scan. So the DB indicates that it is density based. That is like each it tries to identify in the like among the observations or in the data set, it tries to identify regions of high density and regions of low density. The points which appear in regions of low density, those it calls uh, as the anomaly or the outliers. So what it does is the basic idea is for every point you have to identify the neighbors in the feature space. By feature space I mean like in the space of the observations, not location or anything like or time or anything like that. I mean DB scan is not specifically meant to be for spatiotemporal data. So it is, though it is frequently used. So what is done is like we identify the neighbors in the feature space of the observation space and then add in the same cluster. So for example, let us say I start with this point at random, just at random, and among its neighboring locations, I mean the neighboring, not neighboring locations, among the points having similar feature values, say I find that these and these are close enough to it. That is, their distance is like within a threshold. Again, by distance, I do not mean geographical distance. The distance here, basically, this is the space of the measurements. That means, so here, if they like since this is the 2D space, so it indicates that these are actually 2D measurements at every data point we have measured two values, and these distances are also measured accordingly. So if these 2 points are considered to be, or maybe this point also are considered to be close enough to this point, we just add them in the cluster. Then once, so like these 4 points are now together in the cluster. Now we see if we can grow the clusters by considering further points which are close to some of these 4 points. So this point, this point I find it to be close enough to this point. So I add it to the cluster. And see, then this point again, I find it to be close enough to these 2 points. So this also gets added to the cluster. This point is close enough to this as well as this, so it is also added. This point is close enough, so it is added, but we cannot add any further point to it. So these are like these points in the middle. These are called as the core points. That is, and these yellow points, these are called as the border points. They are called the reason why they are called as border points is like they are still part of the cluster because they are within the they are close enough to a core point, but like it does not have sufficient neighbors. That is, like this point itself it does not have any neighbor beyond the points which have already been considered as core, which uh, with which it is close enough. So it's like basically uh, like if you want, you take this point in the cluster, fine, but this point will not be able to bring any more neighbors into the cluster, so the process stops there. So that's why this is called as a border point. Similarly, this is also called a border point. Okay, now this point on the other hand, like although it was discovered late in the searching procedure, it has several neighbors among the other points, so it's not it's still considered as a core point. Now this way, once you are given a large number of points like this, what you will do is you will start off with every point and keep on growing the cluster by this in this way, as long as you can, as long as more points are getting added to it. If this way all the points keep in the data set get attached, that basically means that there are no outliers. uh, Alternatively, it can happen that you form one cluster like this, the clustering stops, you are not able to add any more point, so you consider some one more point here among the other remaining ones, and again you keep on growing the clusters like this. So finally, if you find that at when this process stops, if you find that there are some points left which could not be added to any of the clusters, then those are the anomaly points or the outlier points. So that is the DB scan algorithm. So, but qualitatively, it is not much better than the threshold based case which we are considering, because here also a threshold is required, and if once again if there are bulk anomalies, it will still not be able to capture, because those bulk anomalies itself will be considered to be as one cluster, and you will not be able to like identify that it's not a normal cluster, but it's like an extended anomaly. So there are situations. So as far as spatiotemporal dataset like this is concerned, the DB-scan algorithm goes like this. So now every data point has spatial and temporal neighbors. So unlike this situation where we are all data points are just some measurements with no other attributes attached, so here each data point has spatial and temporal neighbors. So now we will add a criteria that each data point can join only the clusters of its spatial and temporal neighbors. That means even if 2 points are close enough in the feature space in terms of measurements, if they are not spatially or temporally close to each other, we will not add them in the same cluster. So the reason for not doing it is okay, okay, based on this data set, can you tell me why we will, if I have to run DB scan on the on this data set, why I will not consider uh, neighboring point, I mean 2 points to be in the same cluster, uh, like even if they are not spatially or temporally neighbors? The original DB scan algorithm does not say anything about spatial or temporal neighborhood. It only says that if the measurements are close enough, you add them in the same cluster. So in this case, like, can you spot some situation in this dataset? Can you spot some situation where adding 2 points in the which have similar values in the same cluster will be a problem? Say, consider these points, these 2 points, 29 and 30. Their values are very close to each other. Their measurements are quite close to each other. Just one difference. And so we can assume that that is within the threshold. But should I add this and this as part of the same cluster?
There are two spatial groups, S1, S2, S3 are spatially correlated, and S4, S5, S6 are
Yes,
spatially
exactly. So it's like it's like there are two different systems are involved here. So like two locations, like suppose you have two observations at two locations which are far away from each other. Even if they are those observations are close to each other, we cannot really say that they are part of the same cluster or they are part of the same system, because simply because it may be that is the similarity of their values may be just coincidental. They are part, actually they are part of two different systems. Like today, the temperature in Kharagpur, let us say, is around 25 degrees Celsius. It may also happen that today the temperature in, say, in Rome or in Berlin is also 25 degrees Celsius. So should I add Kharagpur and Berlin in the same cluster? Obviously not, because they are part of different, like they are so far apart. Obviously, they are parts of different climatic systems. It does not serve any purpose to add them in the same cluster. So that is why in this case, we will modify the DB scan algorithms such that two data points, like each data point can join the cluster of only its spatial or temporal neighbors. Joining any other cluster is not allowed. The whether it will join a cluster or not is on the basis of the values, but it can join only such clusters where its spatial or temporal neighbors are present. And if it cannot join any such cluster, then we will call it as an outlier or an anomaly. So, if so, like I leave it as an exercise for you to actually try the DB scan algorithm on this data set and see what happens, which for different values of threshold, what are the like which are the points which turn out to be anomalies, and whether you agree with the results or not. But one thing will be more or less clear, that even DB scan cannot handle the bulk anomalies. There is 30 and 31, like they, like you will end up connecting these two and then these two and then these two, because they are spatial and temporal neighbors and they are observational wise they are quite close. Since DB scan does not have this concept of, say, the spatial mean, the temporal mean and things like that, you will not be able to identify this deviation. You will simply think that this is also some cluster. Right. So that's the so that's a limitation of the DB scan algorithm. So how do you get across this kind of limitation, especially if there are bulk anomalies? So one possibility is to consider multiple spatial or temporal scales. So in these, like here, these are the different locations. But what if I merge these two locations and sorry, I mean these are different time points. These are different locations. So what if I merge these two locations? that is, instead of considering S1 and S2 separately, what if I like coarsen the grid? That is, instead of considering these locations separately, what if I take their average? Similarly, for these two locations also, what if instead of taking them separately, what if I consider their average and so on, right? So, like in case of S1 and S2, I find that so like if you do the means, then this is what you what turns out to be like. So here you find that an anomaly has been spotted at time t5, that is basically here. So it's saying that on at this time point, there seems to be an anomaly at there seems to be an anomaly, but this anomaly is actually spreading is spanning two locations and three time points. That is not reflected here. Similarly, another problem that arises here is that if you this 20, this was considered to be an isolated anomaly. But if you take the mean of S2 and the readings at S2 and S3, so here you see that 29, like this anomaly gets absorbed with this 29 value, and it no longer seems like an anomaly. So it's become 25. So, so in some cases, like the bulk anomaly case, it still could not, like it could only partially identify, but like it could not like measure its full extent. But on the other hand, the isolated anomalies, they got just absorbed, and now they are not even recognizable. So this, like, while this can be a good idea, this considering or doing the anomaly detection at multiple scales, but it is not without its risk. Okay, so this is one possibility, that is you coarsen the data set, coarsen it either spatially or temporally or both, and in the way and and you may do multiple rounds of coarsening. In one round you may, from S1 S2 S3, in one round you are making it as S1 S2 S2 S3. In the next round you may take the mean of these also and make it S1 S2 S3. And even although these are parts of different system, so like you may not know that, so these also you may end up like coarsening and so on. So the problem with doing this kind of thing is that we have already discussed what are the various problems. Like when we are smoothing or when we are coarsening out data, we are essentially losing data. So why we may be able to identify some anomalies which appear at like large scales, large spatial and temporal scales. Those may continue to those may actually be visible if we coarsen the data, but in the process the smaller or more localized anomalies may get smoothened out. So that's one problem. The another alternative, or which may be a somewhat more foolproof approach, is to consider the latent variable models. So at every spatiotemporal location or corresponding to each of these measurements, you define a latent variable or random variable called ZST. So this ZST, it can take like either it can take two values or three values. That if it is two values, then the two values might be anomaly and no anomaly. And the three, if it is three values, it may mean no anomaly or positive anomaly or negative anomaly. Okay. So depending on what is the nature of the data you are considering, like you can consider either of these two things. Say, for example, if you consider if the variable which you are measuring is rainfall, then in case of rainfall, there is no such thing as a negative anomaly. Like it is like if there is some very heavy rainfall on any given day, suppose at a given location, on one day there is 150 millimeters of rainfall, we will consider it as a like a case of extreme rainfall, that is a positive anomaly. But if it is 0 millimeters, that is completely dry on any given day, so even if like it is less than the mean, we will still not call it as an extreme event, or an we may not call it as an anomaly event. right? So in this case, in for this variable, it does not consider or it does not make much sense to consider a negative anomaly separately. But if it is a temperature, like it can be like if it is on some day, if it is 45 degrees Celsius, we may call it as a positive anomaly. If another day it is suddenly 15 degrees Celsius, we may call it as a negative anomaly. So like it all depends on what kind of data you are looking at. So now, so like in this situation, ZST, as I said, is a random variable which can take two or three values, and the measurements XST, these also we imagine them to be a random variable. So in case of the parameter estimation cases, we had this is what we had said, that or in case of the geostatistical equations, we had considered that the observations which you have, we will not consider them to be just fixed values, but we will consider them to be realizations of a random variable. So XST we can consider to be like to be following a particular probability distribution which is corresponding to, or which is typical of that location, that time point, and the corresponding K, that is the corresponding ZST. So why is K important? The K is important because if it is like, so K basically tells us whether there is some kind of anomaly or not. If there is no anomaly, then XST will take some kind of values, or or some range of values. But if K is something else, that is if K is saying that there is an anomaly, then XST can take other values also. So which probability distribution XST follows will depend on whether there is an anomaly or not. Okay, so like for example, if you consider one particular location, and if you see like if you consider the like only one thing, so one dimensional observation. So let us say that these are the different observations which you have seen so far. Okay, so so that means that most of the observations are here, but there are some observations here also and here also, etc. So so like we can say that like basically there are three probability distributions associated with this place. One is here, one is here, one is here. So if it like this is the case of no anomaly. This is the case of positive anomaly, and this is the case, and this distribution corresponding to negative anomalies. So now at this, once you have got these like distributions, now suppose you are given a new observation here at the same location. So now so this is the new value of X. So now you have to understand what is the corresponding value of the Z. I mean, is there an anomaly, or like is it part of an anomaly or it is not? So for that, what will you do? You will see under which distribution, under which of these three distributions this is most likely to appear. Okay, I mean it has the maximum probability of occurrence, and most likely that it will have like it. Obviously, it has very low probability under all the distributions, but it may turn out to be that under this distribution, it has a slightly higher probability than the others. So which in which case will imply that this is a negative anomaly. But if you consider this observation or this measurement, so here you will find that this has slightly higher probability under this distribution compared to this or this. So in that case, I will say that this is part of this distribution, which means there is no anomaly and so on. Okay. So also like when we are assigning the value of ZST at any given location, it should be done not only on the basis of the that corresponding observation, but also based on the Z values of the neighboring locations. that is because especially when we are considering the case of bulk anomalies. So if you are considering isolated anomalies, then it is fine to consider only like single locations or single time points. I mean, values, you can consider the values individually. But if you are considering the extended anomalies, then you should also consider the these local, like I mean the spatial or the temporal neighbors. Because if one like the whole idea of extended or bulk anomaly is that whenever one location is having an anomaly, its surrounding locations may also have an anomaly. So suppose the situation like is here. So suppose you have this observation. Okay, this is your observation. So the let us say this has almost equal probability under this distribution as well as this distribution. That is, it is equally likely to be a part of a negative anomaly or no anomaly at all. But if you consider the surrounding location, let us say in the surrounding location, the situation is like this. You have like that this is the negative anomaly distribution. This is uh, the no anomaly distribution, and this is the positive anomaly distribution. And the value in the neighboring location is this thing. Okay. So which is which is pretty much part of a negative anomaly. So since its neighbor is having a negative anomaly, and this one and this location has a value which has some chance of being in the being part of a negative anomaly. So then by taking in the by considering the influence of this neighbor, I will actually say that this is part of the negative anomaly. Even if I consider, like if I consider this individually, I may not find much reason to consider it as a negative anomaly. I may as well consider it to be a normal observation. But if I couple it with the fact that at the same time point a neighboring point is having an anomaly, then I may increase the probability of calling this as a negative anomaly. Okay, so now basically the task is as follows. At every location, you have to define these kinds of parameters for the probability distributions. Again, what kind of probability distributions you will use, what parameters you will use for. So for that, we have to use the parameter estimation techniques, which we have already done. So once at every location, I have identified the normal distribution as well as the anomaly distribution. Next, at any new whenever any new observation comes there, I will have to estimate its corresponding z value, which indicates whether it is having an anomaly or not. And if an anomaly, then whether is it a positive anomaly or a negative anomaly. Okay, so this process of estimating the values of z based on the observation and based on the parameters, this can be done through the process of Gibbs sampling. So what this Gibbs sampling is, I will not go into. It's basically a sampling based method in which enables you to estimate the posterior distribution of various random variables that are which are closely coupled with other random variables. So like once you do it, so now let us take an example. So take this example, just a second. Yeah. So at consider at a like at a location xst like st, I mean location s and time t, the observation is this thing 34.3. Now, if you consider the distribution of like no anomaly and anomaly cases at this location, the it's both are Gaussian distributions, but the normal distribution, that is the no anomaly distribution, it has its mean 30 and its variance is 10. And its anomaly, in case of anomaly, its mean value is 8 and its variance is 20. So then you have to see this 34.3 fits into which of these distributions. That is, we like under which distribution does this value have a higher probability. So for that, you have to use the PDF of the Gaussian distribution to evaluate these things. So these you can evaluate using the PDF, the Gaussian distribution PDF. These also you can do in the same way. Okay, so based on it, you have to estimate what is the probability that at this location ZST is equal to 1. That is, what is the probability that there is no anomaly here based on the fact that you know what is the observation here. So here, so to calculate that, you have to make use of the Bayes theorem. So this is giving you probability X given Z. Now you have to convert it into probability of Z given X. So we know like what the Bayes theorem tells us. Bayes theorem says probability of Z given X is proportional to probability of X given Z times probability Z. Right, so probability, so this probability you are getting from here itself, that is different values of z's are associated with different Gaussian distributions. So for the non-anomaly distribution, you can evaluate this PDF, and for the anomaly distribution, there also you can evaluate this PDF. And what about P of Z? This is basically the prior probability of the different classes. So in this case, there are two classes only, no anomaly and anomaly, or maybe three classes, no anomaly, positive anomaly, and negative anomaly. So what these probabilities are, that will vary, of course, from one location to another and so on. But in general, we do not expect, I mean, anomalies are rare things. That's why they are called anomalies. So most likely this thing, the no anomaly case, that will have the maximum probability. So it may be that probability Z equal to 1 is something like 0.8 or 0.9, and probability Z equal to 2 is 0.1. Okay. And also, like when you are like calculating the probability of Z, then as I said, apart from considering the impact of X, I mean the corresponding observation, we should as well as the prior probability, we should also include other factors which are like saying that we can write it in this way. Probability Zs given Zs say S prime, where S prime is a neighboring location of S. Okay, so if Zs prime is having an anomaly, then the probability that Zs will also be an anomaly, this will immediately go up, and vice versa. So this way, this is an approach which allows you to like calculate the or to fix some probability distributions at all the different locations, like one distribution corresponding to the no anomaly or normal case, and another distribution corresponding to the anomaly case. And based on that, you have to use the probabilistic inference to find which locations are having anomaly and which are not. So and because you are considering to assign in while calculating the value of Z, because you are considering these things, that is the effect of the spatial neighbors and so on, so you can now expect that you will be able to capture the bulk anomalies as well. So this is the one way which can handle the bulk anomalies. So this kind of approach is usually used to identify anomaly events like heat waves or droughts, which are basically bulk anomaly events, which like impact a large number of locations, and also which span several or a long time. So those things it's difficult to identify them on the basis of clustering or any threshold based heuristics. But this is one way in which the latent variable model is one way in which such anomaly events can be identified. Okay. So that's the story of anomaly detection and anomaly event detection. And now let us come to the last topic of this module of data, like spatiotemporal data mining. So this is called data assimilation. So what is this data assimilation? What is assimilation? Assimilation is a process where, like, you have that is say for like in case of biology, you may have come across this term assimilation for in some cases, like say our the human body like assimilates energy from food. That is, food is supplied to the human body. From that, it uh, takes out the energy or whatever the other nutrients it needs, and it incorporates those things into itself and becomes stronger. That is the in the biological situation, that is called assimilation. But here we are not talking about food, I mean energy or nutrient assimilation. I am instead talking about data assimilation. So what can data assimilation mean? So as we have discussed briefly in some of our earlier classes, people can build various models for various geophysical processes. So like we have talked about these process based models earlier. So these, or we have also talked about statistical models earlier. So that is so basically these kinds of models are used for generating or simulating these processes, for generating artificial or fake data which reflect the statistical properties of these things. They can also be used for forecasting. That is, given the weather conditions now, I run a some kind of a weather model which will take the current like the current weather conditions as the initial condition, do various calculations, and make a projection of after half an hour how the weather condition is going to be, how after 1 hour how it is going to be, and so on. So these kinds of things are on the, like, predictions are done based on the basis of models which I said earlier while we were discussing about stochastic rainfall generators and stuff like that. So these models which we are talking about, they can either be dynamical I mean physics based models based on differential equations, or they can be statistical models based on probability distributions. But whatever it is, all the models will have various parameters, right? So and in most situations there is no very good way of measuring those parameters. So what we do is, like, obviously we have to do the parameter estimation on the basis of data. That is, either the parameter values are fixed and they are supplied by some experts, or they are to be estimated from data. So the like, of course, the experts have only, like, even the best expert will have only limited knowledge about all the things, and especially if it is a dynamical thing which where the parameters keep changing, then it is of course even more difficult like to specify the parameter values. So the only way out is to take the help of data. So like when we are studying parameter estimation also in early January, like what we are doing is basically we were trying to choose the parameters in such a way that the likelihood is maximized. But what is the likelihood? Likelihood is nothing but the probability of the observations. In fact, we had said that since something has been observed, then its probability must be high. Otherwise, why would it be observed? So, we must choose the parameters in such a way that the probability of all the observations is as high as possible. So this is, in a sense, this is already like data assimilation. That is, you have data, you have a model, you are incorporating the observations into the model and enriching the model. And this enrichment will help your model to make further predictions. Once you have got further predictions, then maybe you can evaluate those predictions against the data when they become available, and then you may think that, okay, so this my model was still not up to the mark, so you can further tune the model and you can just continue doing this thing. So this is like, so like in a nutshell, this is what is we mean by data assimilation. And the it is particularly challenging if when we have to do this kind of data assimilation in the in real time. That is, there is a model which is running at every stage, it is making a forecast, and then observation is coming in, and accordingly you see that there is a discrepancy between what the model had predicted and or had forecast and what you are observing. Accordingly you have to like make certain changes to the to your model, and this is like a continuous process. The like as you keep on receiving data, you predict the next data point, then you like once you get the data for that point, then you like see that there is a discrepancy and you like update the model state. So it's so this so every model basically has its own internal state. The internal state will can include the parameters, and it can also include various other random variables which we may consider. Say for example, like here, like we are talking about these z variables, right? These z variables are like the internal variables of our model, which is indicating the presence or absence of an anomaly event. Okay, so so there are three things. One are the model predictions, which is shown as or the model forecast, which is shown in green. So the model predicts something along and along with it, it also provides an uncertainty. It says that this is the most likely value of the of whatever we are measuring, but I cannot say for sure it is going to be this only. So I will specify a range within which it must appear, or it is likely to appear. Okay. And then there comes the truth, the actual observation, which is indicated by the star. And you see that the star is actually quite far away from what has been predicted by your model. So that means what? That means there is a discrepancy. So like it may mean that your model is wrong and it needs to be updated, but it may also mean that what you have measured, the your observation, that also is not perfect. I mean, you can always make mistakes while observing the data, especially when like when we are dealing with Earth system observations. So you will have to change the internal state of your model, so that like which overlaps with both what it was originally predicted and what is observed. So note that this range, the initial range of the forecast and the like the range of what is like what the observation is, are disjoint, they do not overlap. But when we are making this red node, which is like basically the analysis, here it's like the range of feasible values is overlaps with both this as well as this. So it's like saying that like you are making a compromise between the observations and the and what was originally forecast. Okay, so once you have done that, once you have is like so this estimating this red is like basically updating your model, taking after taking into account the new observations. So once you have updated the model, then of course you will use it to make another a new prediction, because that is the purpose of your model. Your model is here to make predictions only. So based on this new state, suppose it makes this prediction, but you find the observation to be here. Okay, so once again there is an error. There is no overlap between what was predicted and what is observed. So again, the system state has to be updated to so that it like it kind of forms a bridge between what was observed and what was expected, and then this process goes on. Okay, so like it's like solving the problem of this forecast in a probabilistic framework, and like whenever each forecast is being made in the form of a probability distribution, a probability density function, and and whenever the system state is being updated accordingly, there also you can see that there is a probability distribution. That is, I am never saying that my system state is this. System state means what? System state means the values of the different latent variables as well as the different parameters. So I am never saying that these are the precise values of my latent variables and on my parameters. I am defining a range of uncertainty like this. So that means like everything is being considered as some kind of a random variable where we are specifying not only its mean but or its mean value but also its variance or its uncertainty. So this is basically the way in which the and these PDFs have to be, we have to constantly update them as more and more data comes in. So this is basically the problem of data assimilation. Now like what we is like what we really want to do is we want to uh, like make sure that the predictions are such that whichever like at least the that is it may not be possible for me to make the exact predictions, but at least I can make sure that the like whatever is observed that will have a high probability under my model. Like if you see here, the my model had predicted that the value is going to be in this range, but what it was actually observed was far away from that range. So that I do not want. I want to make predictions which should be as close to the observations as possible. Yeah, which also means that those values which are likely to be observed, they should have high probability under whatever model which I am building. Fine. So now how to construct these models or rather given a particular model, how to keep updating it. So as more and more data comes in. So that's it's a difficult question and various people have tried to solve it in different ways. And like the curse of dimensionality is a huge problem here. The more like if you have a single measurement that is a scalar valued measurement, then that is fine. But if usually or in many situations of earth system sciences, the measurements you have will be like many dimensional, very high dimensional. In that case, estimating these kinds of probability is quite difficult. Okay, so now in our in whatever model which we are considering, so let us consider the or let us represent the model state as like using the variables x. Okay, and the model state will have different values at the different time points. So in this case, the model state includes both the latent variables as well as the parameters, and those parameters also we are considering to be as latent variables only. That is like not only the z's but even the mu's and the sigmas, the parameters of their corresponding distributions, even those will be considered as the like the model parameters which are not observed but they keep varying over time. And the observations at every given time we will denote by these z's, z1, z2, etc. Again, there is no specific, we are not specifying what kinds of observations these are. Are they scalars or are they vectors or are they matrices or what they are? And then additionally, there are inputs at every time point, U1, U2, and so on. So these are things that like at every time point, which are supplied to your model. So like it's like at every time point, your model takes in like your model is at the stage of like is at the state xt. It receives the input ut, it combines them and and provides the observation of the output which you call as zt. And this is your observational model. And then the model's own state will also change as it receives the more input. So like if xt is its state at time t, then at the next time point its state will become xt plus 1, which is a function of the current state as well as the input. So those of you who have studied recurrent neural networks can immediately see the similarities between these. So here it's like the xt is the hidden state which keeps on getting updated. At every time point input comes ut, it results in the updation of the hidden state, and it also results in the creation of the corresponding observation. Okay, so this is your model, but of course we neither know the functions f and g, nor do we know what are the like these variables x and so on. The z's are known to us, the observation z's are known to us, and the inputs u are also known to us, but the other things are not known. Now, for our benefit, the functions f and g, of course, we will specify beforehand. Otherwise, there will not be any way of solving the problem. So now, based on this, there so if like so, these can be either linear or non-linear. That is that is these functions f and g. Like either it can be a linear model, like somewhat like this. Either it can be a linear model like this, or it can be a non-linear model also. And similarly, so this is one important part, the observation model, and this is the other important part, the state transition model, how the system state keeps changing from time to time. So based on this, we can define three problems. One is a filtering problem, where you have observations from Z1 to ZT, based on which you want to estimate the system state at xt. That is zt is your is the latest you have observed. Based on that, I mean t is like you can say is the current, is the present, and based on the present and past observations, you want to understand the correct current state of the system. That is your filtering problem. Next is the smoothing problem. That is, you are given the observations till a particular time point. So based on that, you are trying to estimate past values of the system system state. So you have observations till say capital T, which is beyond T, but you still want to estimate what was the system state at time T. Okay, so that is the smoothing problem, where you are basically doing something yeah, a hindsight kind of analysis. You have data till a particular time. Now you are trying to understand what was the system state sometime in the past. And the obviously the remaining thing is the prediction problem, where based on data up till a particular point, you are now trying to predict what the system state is going to be in future. Then I mean not far future, but in the immediate future. So these are the three important problems which are associated with data assimilations. Okay. Right. So, but so far we have not shown how to parameterize any of these like these kinds of models. So what we are now going to discuss is the Kalman filter. Now, Kalman filter is a very well-known dynamical model which has been which is used in many kinds of applications. I mean, not only in earth sciences but also in say things like computer vision. So those people of you who have some experience with computer vision may know that there is a problem called tracking. Does anyone know what is tracking in computer vision? Has anyone done any project or something like that? No? So it's like you have a video, say let's say a surveillance video from a surveillance camera and so on. And so the tracking problem is that you have to uh, as the name suggests, you have to track the movements of some person or some car or something across the frame, like across these frames. That is, one thing is you can do like at every frame you can try to detect like say the different persons or different cars who are present. But in case of tracking, you actually have to associate that okay, these are like in frame 1, these people were present and they were present in these locations. In frame 2, these people are present but they have moved to some other locations. So now which is like person 1, which is whereas person 1 moved, whereas person 2 moved, whereas person 3 moved, and things like that. So that is the tracking problem in case of computer vision. So in a sense, it's like we are having like having to build a movement, or sorry, a model of the movements of the different persons. So it's like the observations we have are the different frames. From there, and the state which we are talking about are the actual locations of the persons whom we are interested in. So from the frames we have to keep estimating the observation, the actual observations of, I mean, sorry, the actual locations of each of the different persons. Okay, so in this context, the various people, so this is a fairly well-known problem in case of computer vision. People have been trying for at least 20 years to solve this problem. And one of the most or most traditional approaches of solving this problem is using the Kalman filter. Okay. So and it is shown to be doing reasonably also, although it's a simple or straightforward model which does not require so much of machine learning, but it is actually found to do quite well in most situations of object tracking. So what is this Kalman filter saying? So it's, so as I said that, and like these are the two important components of the data assimilation. One is the observational model and the other is the state updation model. Now, so first of all, let us understand the notations here, which I am like showing from this tutorial called kalmanfilter.net. So x hat n plus 1 comma n. So x is the like the system state which is not observed. Like z is the observation or the measurement which is observed, and u is the input which is also observed. So the model, the for the state updation model is as follows. Suppose you are at time n and your and the estimated value of the system is like denoted by in the following way: x hat n n. Okay, so it's like at the nth time, what is your estimate of the system state at the nth time? That is at the current time. So that is what is indicated by x hat nn, and what they are trying to predict is x hat n plus 1 n, that is uh, at time n plus 1 what the system state is going to be like. And why is this comma n there? It's because to indicate that the current time is n, and stand like at this time n you are trying to make a prediction about time n plus 1. So, so this is the model. So, and as you can see, it's the linear model. So it's like saying that the system step at the time point n plus 1 can be obtained in the like in according to the following linear relation, where here you have a current observation. So that current observation, I mean not a current observation, you have the current system step. You transform the system step by using the what is called the state transition matrix. So it this state transition matrix, it's like in a sense it transforms the current value to what the next value is going to be. I mean, this is of course your prediction, not the actual system state. And this anyway the system state is not something which you can measure directly. It's all what's in the like in the conceptual domain. And then the whatever is the input un is also added to the to your this thing to the system state. So so in general the your inputs and the system state will not be of the same dimensionality. So in it might happen that this is a capital D dimensional vector, the system state, while the this your input is only a scalar. or maybe a two-dimensional vector. So like for this purpose, G has to be a something like a transformation matrix, which will like take the two-dimensional or one-dimensional input and project it onto the space of the like basically project it onto the state space. And then there is Wn, which is the process noise. So which is like something, it is something which is unmeasurable. That is you like I mean x itself you are not able to measure. How will you like measure the noise, the hidden noise of the process? But because the like I am not entirely sure about the process, about how the process or the how the system state evolves over time, I nevertheless have this noise to add a source of randomness. Okay. So this is the first part, the state transition. Next is the output, like this model, the observation model. So ZT is a function of XT and UT. So like like in general the UT need not like in most cases the UT is not even used for generating the observations. So it's generally I mean the xn itself has taken in u, so un, so you do not for zn, if you say that zn depends only on xn, it is enough because xn has already taken in un. So this is how the uh, observation is defined, like in the Kalman filter model. Of course, like I am not. So this is, as you can see, it's a linear relation. Usually, I mean there is no reason why it should be a linear relation. It can be something non-linear also. But in case of Kalman filter, the assumption is that there is this kind of a linear relation. And where like so z is a vector or a matrix in some space, and xn the system state, this is another vector or another matrix or something in some other space. So to project, so first of all, for like I need to predict or sorry, the project the system state to the observation space. So for which I use this observation matrix. Okay, so keep note of the different matrices we are talking about. So F is called the state transition matrix, which basically maps the current state of the system to the next state. And then G is called the control or the input transition matrix, so which maps the input values to the system state. And if you consider here H, there is a third matrix H, which is called the observation matrix. That is, it maps the current system state to the state, I mean the current system state to the current observation. Okay. And then so suppose you are trying to like you are at time n minus 1 and you are trying and you have made a prediction about the system state at time n. So how to do that you have already seen. Okay. So you like it's like you are the current time is n, and based on the current time you are making a prediction about the next time, which is n plus 1. Correct. So the idea is that the x hat n so now once you reach that, once that time actually comes, once time n comes, then you will like you may actually be able to estimate the model state on the basis of the observations that you have got. That is, since you know the this observation, in case you know the this H matrix, you may actually be able to form some idea about xn. That is the system state. Of course, you will not be able to know it perfectly, so we'll get basically only an estimate, and that estimate is what I call as x hat n comma n. The hat indicates that it's an estimate, it's not the actual value. This one is the actual value, but this one is only the estimate, something which we are not able to measure. And n comma n, as I said, means the current estimate of the current value. N comma n minus 1 means the past estimate of the current value, and so on. So so like there is going to be some discrepancy between the current estimate of the current state and the past estimate of the current state, and that discrepancy is usually written in this way. So so you like if you can see like uh, so it's like the observation, the current observation minus the projected observation, like at based on the what was considered to be the system state at n minus 1. Suppose I wanted to like let us say at the time n minus 1 I wanted to make a forecast of Zn. That is, uh, I somehow know what is that system state at this time step. I am trying to predict what is or forecast what is going to be the observation in the next time step. So how will I do it? I will obviously do it in two steps. One is I will first try, given that this is my current state, I will try to estimate what the system state is going to be at the next time. For that purpose, I have this kind of an equation, which is the state transition equation. And once I have estimated that, now I know how to map the system state to the output or the measurements. So using this H, like that is, I will basically apply this H on the on my estimate of the system state at the next time point to get the estimated value of the observation. So Zn is the true value or the actual value of the observation at time n, while this is the value which I predict or the output value which I predicted at time n minus 1. So it's like saying that the difference between the between the measured state and the predicted state at time n, this I am trying to express in terms of the observational error. What was predicted to be the measurement at time n and what is actually obtained as the measurement at time n. So these two quantities, these two differences are related by this quantity called Kn, which we call as the Kalman gain. Okay, so like it's a way of mapping the difference in or the error in between the I mean so this in a sense is like we can call this as the forecast error, right? So this is the value which was forecast. And so you are so as a result of, so this was the forecast value, sorry, this is the forecast value at time n, and this is the actual or observed value at time n. Okay, so so this is, that's why their difference is called the forecast error. So the Kalman gain, what it does is it converts the forecast error into the state estimation error. So this is like the so this minus this is like you can say x hat n comma n minus x hat n comma n minus 1. This error is basically the state forecast error. Okay, so yeah, that's how you write it. So just to give a concrete example of what I mean by this kind of a system, so or how a system can be expressed like in terms of expressions like this. So just consider a simple free falling object. So the system state includes the altitude at any given time, whatever what is its altitude and what is its velocity. So like let's denote the altitude by hn and its velocity by hn dot, means the derivative of hn at any given time. And let us so let's say that delta t are the different time steps which we are measuring. That is, at any given time, I am going to make the forecast of where that falling body will be after time delta t. Okay. So my claim is that this is my state transition matrix, and this G, remember G is this the matrix which maps the input to the system state. That is that G matrix is defined in the following way, and the input variable un, that is like the external force which is applied on the falling body at like every given time. So when a body is freely falling, so obviously the only force that is acting on it is the gravitational force. And so so like if you consider the input at any given time, that input is nothing but the acceleration due to gravity. Now, of course, like whether the acceleration due to gravity is a constant or it changes is a different debate. As of now, let us just assume that its acceleration due to gravity is a constant quantity. So, uh, so the input at any given time is, we just write it as g, indicating the acceleration due to gravity. Okay, so now let us see what happens if we write this, like if I write out the different the different equations that we are talking about, especially this states change equation. Okay, so like the state change equation is written in this way. So at any x, so like I leave it as an exercise for you to actually plug in these values and see what the xn plus 1 hat becomes. So basically what we are saying is that given the body's observation and velocity at time n, I am trying to make the forecast at time n plus 1. Okay, and that time n plus 1 is just at a difference of delta t time. That is actual temporal difference is time delta t. Okay, so now if you like you can just verify yourself that uh, what I have essentially written is estimated value. So like sorry, I am calling this as xn. So it's what I am saying is n plus 1 comma n. This I will call as n plus 1 comma n because it indicates that my estimate of where the my current estimate of where the body is going to be at time n plus 1, and this is equal to f times the current estimate of the system state plus g un. Okay, and you can just verify that this is same as what you had written here, excepting for the w. I mean, ideally the w should also be there, but like if we are considering this as a deterministic process, then we can just consider w to be 0. So now, but does it make sense? So you can just convince yourself that if you use the Newton's law of motions, this is what you will get. So the Newton's laws of motions, like this thing, S equal to ut plus half gt square. Right, so it's like so what is s is basically the distance traveled, that is the uh, difference between its altitude at time n plus 1 and its current altitude. So that is to that, like that can be represented that distance is according to Newton's law is ut plus half gt square. What is u? U was the initial velocity, which we call like, which is nothing but this the current velocity at time n, which is h dot, which is represented as h dot. And like the other things just follow from this. So so now you can try like you can see that like the like for the like when you are considering this first equation, that is the updated value of the altitude, then you what you like what this equation is giving you is basically the Newton's this law of motion. And the second component of the system step, the system step has two components. One is the location, the other is the velocity. I mean the instantaneous location and the instantaneous velocity. So at time n plus 1, what we have already seen how to get the current like how to like predict the location. Now I want to predict the velocity. So how the prediction of the velocity according to what is written here is something like this: n plus 1 n h hat is equal to So this 0 and 0 is changed. So h dot n comma n plus g delta t, right? So as you can understand, this is like the initial, like this is the initial velocity, this is the final velocity, this is the acceleration due to gravity, and this is the time changed. So again, Newton's motion v equal to u plus gt. That the same thing is being used here also. Okay. So, this is just an illustration. This has, of course, not got anything to do with our data assimilation or anything like that. You would have noticed that there are no measurements also which are involved in this case. This is just to give an example. So in general, this is how we are. These are the different the vital equations of the Kalman filtering. So like here you are predicting the next state. Here you are. So this is the state transition model, and this is like the observational model, and this is basically the correction model, where you once you get the measurement at any given time, you update your measurements about, or you correct your measurements about the system state, right? It also needs to be remembered that whenever you are making any prediction either about X or about Z, that is associated with some kind of uncertainty. And so that uncertainty is, so like the values which are being we are being talking about here are, in a sense, they are the mean or the expected values. But I also need to quantify the uncertainty. That is, I have to provide a variance also around that mean value, so that I can say that that the system state at the next step is going to be this, or within a radius of something around that value, right? So these things, the I mean the uncertainty have to be quantified with the help of covariance matrices like this. So like I will not go into the details of how these relations are derived. So if you go to this tutorial kalmanfilter.net, you can actually see how these are done. So if anyone is preparing a scribe note on Kalman filters, I will request them to study how these uncertainties are quantified and so on. And finally, this Kn, the Kalman gain term, which I mentioned, that also can be estimated using in terms of these things only, like which we have talked about. So Kn is the Kalman gain. So Pn, and so this is basically the prior estimate uncertainty matrix of the current state. That is at time n minus 1, when I made a prediction about what is going to be the system state at time n, then whatever was so that had an uncertainty associated with it. So that uncertainty is captured by this covariance matrix P. This is the same covariance matrix as what we studied when we are talking about the multivariate Gaussian distribution. And H is the, of course, the observational matrix, that basically this matrix. And then similarly the other things like this R. What is this R? R is the measurement uncertainty. So whenever you are measuring this Z, this is associated with an uncertainty which is coming from this Vn. This is the random noise vector. So so this noise vector, so like we can assume that this is undergoing some kind of a multivariate Gaussian distribution. So its mean value is definitely 0, but it will have a covariance also. That covariance is R. So basically, so I will not go into any further details. So basically, what is happening in case of data assimilation with Kalman filters is captured by this thing. So it's like saying that you have some initial estimates of these parameters as well as of the system state. That is some like whenever you are running any kind of art system model, you basically provide its initial conditions, and then from that initial conditions it keeps on predicting into the future, and those predictions you can update as you keep on receiving more and more data. So once you get the initial estimate, what you can do is you can what you do is, first of all, you extrapolate the state, that is at this is the time n, what is the system state going to be at time n plus 1, and along with it you have the the uncertainty of the extrapolation also, which is captured by this kind of a covariance matrix. So why this covariance matrix is can be expressed in this way, that again like if you actually study this in detail, then you will be able to estimate it. If you go to this website kalmanfilter.net, you will find that it is written it's explained in great detail. So once you have predicted the system state at the next state, so implicitly you have also predicted what is going to be the next observation. Because you have the observational model, which is you defined in terms of the matrix H. So you are saying that at time sitting at time n, you are predicting that the next observation of that is going to be something like this, right? So I am first extrapolating the system state. Based on that, I am extrapolating the observation. Next, what happens is the observation actually comes in. The system state, I like whatever I may have estimated may be wrong, but the system, yeah, the system state I may not be able to, I am not able to estimate at all, but I can estimate the observations, I mean the measure the observations. So based on my, once I get the actual measurements, which I may call as y of n plus 1 comma n plus 1, right? If you want, instead of calling n plus 1 plus n plus 1, I can as well call it as n comma n. Just depends on how you define n. So this way, what I what I can do is, so first of all, so the, sorry, not, I mean, I'm calling it as z. Sorry, so z, right? So once you have got Zn, so here you basically update the, so this is what you have observed, and this is what you had predicted. So this difference, you are able to measure this difference once you get the observation. So this difference you measure, you multiply with the Kalman gain, and you add it with the estimate of the system state, which you had already got at this stage, and then you get your updated value of the system state. Okay. So now how will you get, where will this gain come from? How, where, or how do you know this Kalman gain? For the Kalman gain, you have this equation. So this allows you to calculate the Kalman gain. So then what happens? So now we have obtained the value of the re-estimated the value of the system. So along with it, you have also have calculated its uncertainty, right? I mean, nothing happens with it, nothing is certain. There is always an uncertainty involved, so that you get, and then you again move to the next time step. So if I want to draw the whole thing, it's like saying you initially have some estimate x0. Okay, it's your initial condition. So based on that, you forecast x1, what is going to be the next state. Now, and accordingly, you also predict what the corresponding observation is going to be. You call it as Z1. So let me call it as Z1 hat, because this is only your estimate, not the actual thing. So similarly, this also I will call as the estimate. Now what happens? Now you get the actual value of Z1. Right, the actual value of Z1 comes. Now so what you do is you may compare the the predicted Z1 and the uh, observed Z1 to calculate the error, and using that error, what you do is you re-estimate x1. That is what you had like basically you had got x10, that is sitting at time 0 you had measured, like you had got an estimate of x what it's going to be at time 1. Now on the basis of the observation you received at time 1, you get a refined estimate of this system state which you call as x11. Okay. So now you had got x11. So now what you will do, you will predict the what is going to be the next state of the system. That is, you calculate x hat 21. Why 21? That is the time is still 1, but you are predicting what is going to be going to happen at time t equal to 2. And based on that, you also imply what is going to be the corresponding measurement. But then you get the actual measurement Z2, you compare these two things and you get some error. That error you again propagate back to the the system measurement, and you refine the system measurement to get x22 and so on. You just proceed in this way. So as that more and more data comes in, your estimate of the system also keeps on getting updated, right? So just to summarize it, so like here you predict using this kind of a like you predict the system state using this linear equation, and along with it is also associated this kind of an uncertainty. Next, you update the thing up, like you update the system state. This is was your original estimate of the system state before getting the data. Now you have got the data. So you make a using the Kalman gain contact you concept, you measure what is the system like what is the updated system, and for that also is associated with a this thing with uncertainty, and you just keep on doing these things. So this is the like basically the idea of Kalman filter. And then like you can do the whole thing in a Bayesian framework. So that is, as I mentioned earlier, this is associated with the three problems. One is the filtering problem, the smoothing problem, and the prediction problem. So the prediction problem is like basically how to estimate xt on the basis of the past observations that we have already seen how you can do. That is that's basically what is happening in this case, right? However, like we can actually cast this as a like in terms of probability distributions, and we can like consider these as random variables and do the that is we can that is we can basically, instead of giving a point estimate of what xt is going to be, I mean what the system state is going to be, so we can actually define a probability distribution over it. Okay. And similarly, we can also solve the other problems like the filtering problem or the smoothing problem. So the filtering problem is like given the observation still a particular point, estimate what the observation, the current observation, I mean the current system state is going to be. That is also done again in the that's basically what is happening in this way here in this step. Here you have got the observation and like based on it you are trying to predict what the next I mean what the current system state is going to be. But but what you have written in the form of this kind of a linear equation here, can you express it in the like in terms of a probability distribution and so on. Similarly, you can solve the prediction problem also. And so so basically like what like you might get some kind of a like sequential data. I mean, the observations might come in the form of a sequence. So, like while you are dealing with the sequence, you have to utilize various properties of the Bayes theorem. So like whenever you get a sequence like this, you can actually break it down, break it in this form as a so you know that uh, x x1 is independent And now x2 depends on x1, then x3 depends on x2. This is the way the whole system is evolving. So if you are given the sequence of states like this, from x1 x2 up to xt, you can write it as like as a product like this. So it's like saying the probability of the first system value times probability of x2 given x1 times probability of x3 given x2, and so on. Right, like you can express the state sequence in this way. Similarly, if you are given an observation sequence given a state sequence, that also you can formulate it in this way, because at any state the observation depends only on the system state at that time. That is, like the system state evolves like this from x1 to x2, x2 to x3, etc. And correspondingly we have y1, y2, etc. and so on. So at any given time, y1 depends only on x1, y2 depends only on x2. So whenever we have a joint distribution of all these variables, we can actually so we can say that y1 that is given these sequences, y2 is independent of y1. Y2 depends only on x2. So once x2 has been given to you, y2 is independent of y1. So you can, so like we know that the probability of a joint distribution can be expressed as a product of their marginal probabilities. So you just write this thing as a product of these probabilities. Okay, and so like you can do it in this way. Okay, so I am not going into the details of like what kind of probability distributions are used in this case and so on. And so, yeah, so basically that's the whole idea of data assimilation. Sometime in March, we will have a guest lecture by Professor Amit Apte, who is from IISER Pune, who is an expert in data assimilation. And so he will actually give us an example of how an art system model works, and how its parameters are updated with the help of observations using this kind of a Kalman filter model. Okay, so with this we come to the end of today's class, as well as this session on this module of spatiotemporal data mining. And as I said, so on next Monday we will have a numerical problem solving session, and your first assignment is also due next week, and your exam will be held on the following Monday, which is will be 21st of February.